Okay. Thanks.
Okay, thank you very much, Mircea and Codina, for the invitation to this summer school. I'm sorry not to be in person with you, but today I will try to share some kind of overview of some works that concern systems with Coulomb and Riesz interactions and various aspects of them. I'm sure that it will overlap with some things that you've heard this week, but maybe that's good. And also there will be hopefully some other non-overlapping things. So this is what I want to look at. I remind you the Coulomb kernel, interaction kernel is 1 over the norm of x to the power d minus 2 in dimension d, as long as the dimension is bigger than 3. But if you're in dimension 2, then it's minus log of norm x. And if you're in dimension 1, it's minus norm x. Okay, so there's a slightly different behavior. And so a Coulomb system is a system of n particles that will live in Rd, let's say, the Euclidean space, with this Coulomb pair interaction. So you sum all the pair interactions here. And we add here a confinement potential because we want to be in Euclidean space. So this is to keep the particles sort of in a compact set. Okay, so for that you have to assume that V grows sufficiently fast at infinity. And you have to put an n in front so that this term is strong enough to balance the repulsion term here. Okay, now I told you about Riesz systems, and that corresponds to the case where you generalize to, so there's going to be 2 cases, the logarithmic interaction in 1D, which is not Coulombic. So you can call that a log case, or inverse powers, 1 over x to the s, where s is different from d minus 2. That will be the general Riesz case. Okay, so I will be discussing briefly 3 different kinds of questions that you can ask. One is look at minimizers of these energies, or maybe critical points of these energies, Hn. Understand evolution equations. So here I wrote 2 kinds. One is the gradient flow, where each point moves with velocity xi dot equal to proportional to the opposite of the gradient of the interaction energy with respect to the entry xi. Okay, so this is a gradient flow, and here it's normalized by the number of particles, which is a good normalization, a natural one, let's say. More physical is even to look at Newton's law, where the acceleration is proportional to the gradient, to the force, if you want. I will not have a lot of time to say stuff about this, but it's also very interesting, and we also have some results. And the third setup is to do statistical mechanics and to study states with temperature. Okay, so I will describe that as well. Why are we interested in such questions? Very brief overview of motivations here. I think in this audience, you know about this one, certainly Fekete points and approximation theory. Minimizing these types of energies can be useful to distribute points, good distributions of points. Also distributions of points that approximate well an integral. So if you want to approximate integral of a function by a Riemann sum, where do you put the points? And these are called Fekete points. In fact, you can look at these problems on closed manifolds, often on spheres, and you find that you want to maximize the product of the distances in order to distribute your points optimally. But maximizing product of distances, that's equivalent to minimizing minus sum of log of the distances. So you refine the question of minimizing log interaction. And people study these things with weights, right? Like an exponential weight here. And then if you take the log of this, you're trying to minimize exactly the same interaction energy plus confinement potential. So there's a large literature on this in the approximation theory community. So this is a picture that doesn't work. But, so more generally, people are interested, as you know, in minimizing risk energies. So general inverse powers of the distance that you can do on a manifold that's compact, so you don't have boundary problems or infinity problems. And that gives you a whole family of problems, which connects the logarithmic energy, which can formally be seen as the case where S would be taken to 0 or tending to 0. So on the one hand, you have the logarithmic interaction energy, and on the other hand, when S goes to infinity, you actually retrieve the best packing problem, which is the problem of packing the space with the maximal number of hard spheres. And this is a solution in 2D. Okay, second motivation, maybe less familiar in the points community, but it's from physics, condensed matter physics. When you want to look at models for superconductors and superfluids and Bose-Einstein condensates, you study PDEs, in fact. So you start by studying these types of PDEs, which look a bit like Schrödinger kinds of equations, nonlinear Schrödinger or heat equations. And psi here is a complex valued function. And it turns out the interesting objects are the vortices, which are the zeros of this complex valued function. And now you're back to points, or at least you want to understand these zeros. You want to understand actually in the asymptotics of this parameter here, epsilon going to 0, you can really describe things in the limit in terms of points. So this is large literature on this. And you find that in the end, these points, these vortices, they interact with the logarithmic interaction in 2D. So you're back to this logarithmic system. And this happens also in classical fluids, where you have vortex interaction in fluids, in 2D fluids. It's also logarithmic interaction. Okay, so here's a picture of what happens in superconductors, which I told you about briefly. You do see these vortices, and you see that they form these triangular lattices, beautiful pictures that are experimental. And this is called the Abrikosov lattice in physics. So it was predicted by Abrikosov from the phenomenological model of Ginzburg-Landau, and then it was observed in experiments. Okay, so of course, this is part of the puzzle to understand, explain these lattices. Okay, and third motivation is statistical and quantum mechanics. In this motivation, it's a reason to study the model with temperature. These Coulomb systems with temperature correspond to toy models for matters, correspond also to the laws of eigenvalues of random matrices, to some quantum mechanics models, some theoretical physics models. So there's also a large literature on this in statistical mechanics. So I will describe towards the end the model with temperature. Okay, if you want me to stop and expand more on something, I can certainly do that. Okay, so let's go back to the beginning. We have these energies. We want to consider large numbers of particles or of points, and you want to understand first thing, what is the macroscopic distribution of the points when n goes to infinity? Also the microscopic behavior, and things like the minimal energy. What does it look like? How does it expand? So you certainly know these types of questions, right? To prove, for instance, here that the minimum of the logarithmic energy on a sphere has an expansion in n, in powers of n, but also involving log n. And it's still an open question to describe all the coefficients in this expansion. So for now, finding the coefficient A is easy. We can access the coefficient B. But beyond that, I think it's still completely open. And it's related somehow to Smail's problem, Seven's problem. Okay, so I will review a little bit the mean field limit, which I suppose is something you know, but just to set up the notation. So the first pass, you want to understand the macroscopic distribution of particles. And another way of asking this question is to look at the limits of the empirical measures, which is 1/n sum of Diracs at all the points, right? So this is a probability measure. It describes the distribution of points. The leading order, this leading order behavior is quite now quite classical. It relates to the Frostman equilibrium measure. So what you do is you write this minimization problem, the one in red here. So I remind you what the energy is. The energy is up here. That's the discrete problem. And instead of this discrete problem, you write a continuum problem on probability densities, okay? So mu here now is a probability density. You double integrate the interaction energy plus the confinement energy. And this problem turns out to be, in fact, simpler than the original problem because it's a convex problem, doesn't have an n. And so it has a unique minimizer. I mean, the existence is actually okay as long as V grows sufficiently fast at infinity to keep the mass together, so to have tightness of your probability measures. And so there is, you know, in good cases, a unique minimizer. So that's the equilibrium measure of Frostman. And you can show that minimizers will converge to this equilibrium measure. So they converge in the sense that the empirical measures converge. And also the minimal energy, once you normalize by n squared, where n is number of points, also converges to the E of this equilibrium measure. Okay, all of this as n goes to infinity. So this, I said I was working with the Coulomb or Riesz interactions. In fact, this is quite general. What you need is that W remains integrable near the origin. So if you're looking at inverse powers, it imposes that S, the inverse power, is strictly less than the dimension. Otherwise, it won't be integrable. So this is what's called the potential case. Right? So if you're in S bigger than D, that's called a hypersingular regime. It's not potential, so you can't describe things in this way. So examples of equilibrium measures, there are some that are well known. For instance, when V is quadratic, the confinement is quadratic, you can expect that everything will be rotationally symmetric. And so for the Coulomb interaction, what you find is the equilibrium measure is just the indicator function of a ball, properly normalized. So it means the equilibrium measure is constant in some ball of correct radius. And that's called the circle law in random matrix theory. You see here points representing random matrix eigenvalues that distribute themselves uniformly in a disk. There's another one that's very famous also in random matrix theory, which is the equilibrium measure for the logarithmic interaction in 1D, and also with quadratic confinement. Then the equilibrium measure density has this form, which is the graph of a semicircle. So it's called the semicircle law of Wigner. And you see here a histogram of eigenvalues of random matrices with symmetry, which distribute themselves exactly, you know, seemingly according to this semicircle law. Okay, so this serves as two models. The equilibrium measure, it looks to be like a measure with the density. I will call mu V both the measure and the density. With compact support, that's true when V grows fast enough at infinity. And on its support, so okay, it can be discontinuous on the boundary of the support, but on its support, we assume it has a nice density that's regular enough. Okay. All right, so I want to talk now a little bit about this dynamics problem. I mentioned the gradient flow problem and also the Newton's law evolution problem. So before doing that, let's talk about the potential generated by a distribution mu. So give yourself some distribution of points. It can be discrete or not. You can form the potential H super mu as the convolution of the interaction kernel with mu. defined like this. So physically, it really has this meaning of a potential, like an electric potential, for instance, if W is Coulomb. And then the total mean field potential that's generated by mu will be the sum of this h mu plus the external potential V. And the mean field force then is minus the gradient of this total potential. And so what you expect for the gradient flow limits, at least formally, now it's less of a surprise maybe that it's this PD. You expect the density of points to solve this PD in the box, dt mu equals divergence of this mean field force multiplied by mu. Of course, this is to be solved with some initial data corresponding to the limit of the empirical measure. So how do you guess this red equation? Well, you remember that on a purely formal level, but in the sense of distribution, it's correct. If you have a moving Dirac mass, if you have a Dirac mass at the point x of t, which is moving, you differentiate in time this distribution. It's equal to minus the divergence of the velocity of the point times the Dirac mass. So this is an identity. Okay, so if you want to guess the equation, you should find a similar continuity equation, something of the form dt mu, so replace the Dirac with mu, equals divergence. Here you should put the velocity, and here you should re-put the measure mu instead in the place of the Dirac. So you see the mu and the velocity field where it's given by this mean field force here. So this is what you expect. Now, it's easy to write this as at the formal level, but to prove it, to prove that you really have convergence as n goes to infinity to the solutions of this PD, that's much harder. It's trickier because, well, first you want to pass to the limit n goes to infinity, and you see you have nonlinear terms, right? And you have a term h mu times mu. So it's nonlinear in mu. And in addition, you certainly have to worry about the singularity of the interaction W, which is an inverse power, typically. So this has been elusive, actually, and for a long time, there were only proofs for the log case, for the 2D log case, or for cases more recently where the interaction, the power in the interaction is strictly less than d minus 2. And if you remember, d minus 2 is the Coulomb case. So this is just sub-Coulombic, right? So it can be singular, but not as singular as Coulomb. And here results in fairly low dimensions again. Okay, the 2D log case was much studied, I told you, because it's what you find for vortices in classical fluids, classical fluid mechanics. And so it had been worked out for that reason. The log case is a bit easier because, well, the log is singular, but not that singular, and somehow you can work with that. Okay, so here is a theorem that actually works for all these Coulomb interactions and also all Riesz interactions that are super Coulombic. So it allows you to go from Coulomb to D, and I told you D is the border of the potential situation. So above D is hypersingular. That's another story as well. And you write, you prove what I said. You take solutions of the gradient flow system with some initial data. You have some assumptions on the initial data, which is that there is no excess of energy. The limit is regular enough. So it's a sort of well-prepared assumption. And you can show that up till a maximal time of existence of your limiting equation, you have convergence of the empirical measure to the solution of the announced equation. Okay, so then it becomes a sort of PD equation. When is this limiting equation well posed? What is the maximal time of existence? And it turns out that in these repulsive cases, it's actually well posed for all time. So you have the convergence for any fixed interval of time. Of course, the rate of convergence will deteriorate as time goes to infinity. So since this result there's been lots of improvements of it. The case with noise was treated in a very nice work by Bress, Jabin, Wang. And there were some generalizations by Rosenzweig, and also Rosenzweig and myself and Hung and Nguyen. We treated a slightly more general class of interactions, including sub-Coulombic as well. And we also proved global in-time convergence in some cases, etc. Okay, so I want to step back for a second, because these mean field results, so these results where you study the empirical measure and find its limit, I told you already, for minimizers, this doesn't really require to be Coulomb or Riesz or anything specific. Some of these, the results that you expect here, this mean field convergence as well, you expect it to hold for very general interactions that are not too singular. So in particular, for example, smooth interactions, that should work as well. That should be even easier. So it is true that a lot of these things work for fairly general interactions. Sometimes we cannot make the whole proof work, but so what is specific to Coulomb that we can use and leverage better is that Coulomb kernel is the fundamental solution of the Laplacian. Right. So if you, in fact, if you ask from the beginning, I should have said this. What is the Coulomb kernel? Why is this? It's because it's the thing that solves Laplacian W equals a Dirac mass up to constants, multiplicative constants. Okay, so what does that mean that it's a fundamental solution to Laplacian? Well, it means that when you take the potential, the H mu that I was talking about, it will solve a nice Poisson equation, because the Laplace operator is it's a differential operator. So the difference between the Coulomb and non-Coulomb case is that when you write H mu, which is W convolved with mu, it solves this equation. So W solves this, and so H mu solves this local equation. Whereas if you were to write general W, you would be solving some non-local equation, some sort of Fourier multiplier, if you want. You could view W as a sort of Fourier multiplier or fractional Laplacian or something like that. Okay, so this is actually nice. It must help, the fact that it's local. And so what we do is the following, and this is the basis of the electric formulation here for this business. For instance, you can form this quantity. So assume you have mu and nu that are two probabilities, let's say, two probability densities or measures of same mass, it doesn't matter. Okay, and then form this double integral, W x minus y, d mu minus nu of x, d mu minus nu of y. So I will call this the norm squared of mu minus nu. So here I can recognize the convolution. So there is the convolution of W with mu minus nu, and then there is the mu minus nu again. So I can express this in terms of potentials, of potentials like this, H mu. So it's H mu minus nu, and then the mu minus nu again becomes the Laplacian of H thanks to this equation. Okay, so up to these constants that depend only on dimension, you find H minus Laplacian H. And so you can use Green's formula to integrate by parts. And now you rewrite this as integral gradient H mu minus nu squared. Okay, so what was this thing? This was a total sort of Coulomb interaction of a system of charges mu and nu, or mu minus nu. It was the total Coulomb interaction of this. It was a double integral, and it becomes a single integral, but expressed in terms of the potential. Okay, so it becomes the Dirichlet energy of the potential H. This is, of course, this is known in physics, not so surprising, but so you can use that, in fact, to define a distance. You see, I write it norm mu minus nu squared, so it's like a distance squared between mu and nu. And And so here I'm going to rewrite it now for a discrete situation. So here I say it's a Coulomb distance, but we also call it modulated energy in the context of the dynamics problem. So here, if you have a distribution of charges capital Xn, or capital Xn is just the collection little x1, x2, little xn, you form the empirical measure 1/n sum of delta xi, and you measure its Coulomb distance to mu, some reference distribution of charges in this way. So in the same way as before. The only difference here with the previous definition is that here I have to do this. You see here I have triangle complement. So here I have to remove the diagonal. The triangle means the diagonal on R2 cross R2, sorry, RD cross RD. And you have to remove the diagonal because if you keep it, then you will have the self-interaction of a Dirac. Delta xi will interact with delta xi, and that will be infinite because W is infinite at the origin. So you don't want to count the self-interaction of the points. You only want to count the interaction of the points with each other and of the points with the measure mu. So you remove the diagonal for that. So this quantity is like a square distance, if you want. This modulated energy is what I used to show convergence for the evolution equations. What do? You plug in here xn. For xn, you plug in the evolving points. And for mu, you plug in mu t, the expected limiting distribution, the solution to your PDE, which you think is the limit. So you plug in xn t mu t, you take this quantity and you differentiate in time. And when you differentiate in time using the evolution equations, you find interesting things. So it's both used for the evolution, but also as a next order energy, as I will show a little bit later. This is explained in the Coulomb case. I explained in the Coulomb case how to do this integration by parts. Here you see the Green's formula definitely here uses the Coulomb relations. But in fact, in the Rees cases, when S is bigger than D minus 2 and less than D, you can make the same idea work thanks to an extension procedure due to Caffarelli and Sylvestre, or at least popularized by them, which allows to do the same as long as you add one dimension in space. You sort of embed your system into a higher dimensional space. Okay, so what is the crucial ingredient that makes a lot of things work is a functional inequality, which now we call a commutator estimate, and which says the following thing. For given a Lipschitz vector field V, so it's a completely general inequality, right? It doesn't use any problem, any PDE or evolution, just a functional inequality. So if you see an expression like this, V of x minus V of y dotted with gradient W x minus y, and then you integrate it twice in the same way as before, this thing is controlled by the modulated energy F itself. So it's controlled precisely. There is an error term here, which is very small, -1 plus S over D. S is the Rees power. So this is actually small. And this multiplicative factor depends on the Lipschitz norm of the vector field V. And I want to just say that this is a plausible relation because if V is Lipschitz, V of x minus V of y has the homogeneity of x minus y near the diagonal. And gradient of W, because W is an inverse power, the gradient of W is like W, but divided by x minus y. And so these two things should sort of cancel, and this should have the formal homogeneity of W of x minus y. And so then it resembles exactly what's on top here, right? If you replace this by that. So it does look like it could be like the energy itself. But it's actually delicate to prove this. And the reason is this removal of diagonal. That's the first difficulty. And the other thing is that even if you do this homogeneity argument that I said, you have a problem because here you have cancellation, so you cannot bound with absolute values. So you have to continue to take advantage of the cancellations. And in fact, what you exhibit in a harmonic analysis sense can be seen as a commutator estimate. So hence the name commutator estimate. Okay, so when you differentiate in time, this thing, I told you differentiate in time, you find quantities, you find nice algebra, you just do the formulas, and this algebra makes you find terms like that. So it comes out like that. Then you use the functional inequality, and you're practically done because you can show that the time derivative of the modulated energy is bounded by the modulated energy itself. And then you finish with ground value. I think I hear a question or something. Is someone talking?
I was wondering, I was wondering if that in the last line in parentheses,
yeah,
n to the minus 1 plus s over d, is it always much smaller than f of xn mu, or are there cases when they are comparable?
So at yes, it's always small. It's always at most the same because so first of all, it always tends to 0, right? Because I assume s is less than d. So it's a negative power of n. And the other thing is that f at the minimum is of the same order. So there could be some, it could be that if you're in a good case, f is of the order n minus 1 plus s over d. And if you're in a worse case, it's even bigger. So this can be considered as a small additive error, I would say.
Okay, thanks.
And for the convergence, all that matters to you is that this is all little o of 1, that you just need that it goes to 0. If you can show that this goes to 0 as n goes to infinity, you have convergence already, right? Because then this thing is almost like a norm, like a square of a norm. So if it goes to 0, you're good. So this term is not annoying. It's actually sharp. It's a sharp error term, and it's pretty good. Okay, so this functional inequality is the core for this dynamics proof. It also will serve a lot for this the static situations, and in particular the thermal situation that I will describe later. So it comes back many times in this approach because it ties very well with this electric formulation. Okay, beyond the mean field limit. So now that we know, what the empirical distribution does, what's next? What's next? So can you describe things at the micro scale? Can you describe the next order terms in the minimal energy? So now I'm going to drop the dynamics. I'm going to go back to the question of minimizing the energy. Okay, and I want to go to the next order this time. And understanding what happens at next order in the energy is actually equivalent to understanding what happens at the microscopic scale. So the microscopic scale is encoded in the next order. I told you the leading order is n squared. It's the equilibrium measure that is well understood. Okay, so to go beyond, you want to continue by expanding energy around the equilibrium measure mu v, and continue to express everything in terms of this electric potential. But so now we're going to do the electric potential of the empirical measure minus mu v. So here I normalized it slightly differently. So this is n times the empirical measure, and this is n times mu v. And then you can write the interaction energy of this new system, which is a system with positive charges that are discrete charges, and a negative charge, like a negatively charged background with mass minus n. So they balance each other. And you can do this Green's formula computation that I did a couple of slides ago and rewrite everything as the Dirichlet energy of this electric potential. Okay, so now that it becomes a single integral, as I told you, in the potential, you can hope to show that the energy is additive over subcubes. And this is actually proven thanks to a screening procedure that allows you to separate boxes and to sort of neglect the interaction between boxes. Even though there's many pair interactions that you have to count, the interactions between faraway boxes, you can sort of neglect it thanks to this screening effect that is done by the balance between the charges and this background, the subtraction of this background charge. Okay, so this is all I will say, but of course there's many details behind this. And then what we're going to do is we're going to couple this with the blow-up procedure. So here you see I've plotted the support of the equilibrium measure, which is denoted here as sigma. And you know that you have endpoints typically in that support. So typical distance between points is n-1 over d. That's the micro scale in dimension d. And so you can zoom near any point in sigma at the scale mu v of x times n to the 1 over d. So this is the zooming scale that will lead you to configurations of points that are typically of density 1. So typically 1 point per unit volume. Each configuration, here a green one, a red one, a blue one. For each configuration, which when n goes to infinity, the configuration starts to fill up the whole space. So you have an infinite configuration of points together with a uniform negative background of density charge -1. So this in physics is called a gelium. Okay, an infinite configuration of point charges with a uniform background charge. And we define an interaction energy for the gelium that we call W. And it's defined, how is it defined? Well, it's a sort of large volume limit of this Dirichlet energy. And then the total energy will be what you take by computing the average W bar of W over all blow-up centers in sigma. So, you know, you have the W of the green configuration, the W of the red, the W of the blue, but now you have to sum them all. They're all equally valid. And you integrate over this whole region to find W bar. So this is all a little bit informal, of course, but that's the idea. And so that's what we find for the next order energy. So this was done in a series of works with Etienne Sandier. First, we did the 2D log case, then with Nicolas Rougerie. We did all the Coulomb cases, then with Mircea, and we did all these risk cases. And so in all these cases, as long as it's Coulomb or super Coulomb, we find an expansion of the energy to next order. So you remember the leading order term, n squared times the E of the equilibrium measure. So this was the Frostman, the first computation that I had showed you. Then there is a term that's in light blue because it only arises in the logarithmic cases. In the logarithmic case, you should take s equals 0, and then you have this n log n term here. And then the next order is n1 plus s over d times W bar. Okay, so this is the factor and this is the prefactor, W bar. So W bar is computed for these infinite blown up configurations, etc. And then the remainder is lower order. We could even quantify a little bit. But so a consequence of this formula is that if you want to look at minimizers of this, because this is constant, so you really have to minimize W bar. And so you can write a theorem that if you start from minimizers of Hn, and if you blow up around a point in sigma, for almost every point around which you blow up, you should minimize W. So the limit configuration minimizes W. I told you W is defined in a semi-explicit, implicit way with the electric potential in larger and larger boxes. Okay, so Betterman and Sandier adapted this to the 2D sphere. So this provides finally the next order coefficient for the expansion of the minimal logarithmic energy on the sphere that had been a sort of conjecture for a while. We proved similar results for the Ginzburg-Landau model, which relates to this Abrikosov lattice. There are some more precise results about equidistribution of energy and of points for minimizers that that you can show by bootstrap on scales. So there was works with Simona Rotanodari, Mircea Petrache, and Rotanodari, and myself and Armstrong. And so this leads us to the question, right now we have a new question, minimize this W. Right? So if you want to minimize the energy, you zoom and you see configurations in the limit, which should minimize a certain W. So what do we know about the minimization of W? Well, we should expect the points to be well distributed, right? This was the starting idea. In dimension 1, it's easy to prove. The minimum is achieved when you put all the points on a lattice, Z. In dimensions 2, 8, and 24, as you know, there is a conjecture called the Coulomb conjecture that says in those dimensions, there are some special lattices. So in dimension 2, it's the triangular lattice that we have seen as the Abrikosov lattice in superconductors. Dimensions 8, the E8 lattice, and in dimension 24, the Leech lattice, that have this universally minimizing property that they should minimize for a broad class of interaction energies. It goes from sphere packing to smooth interaction energies. In fact, with Mircea, we wrote a little note that shows that really, if you can prove the Coulomb conjecture, it applies to our W. So it does work for Rees, Coulomb, singular interactions. Okay, so then there remains to prove Coulomb conjecture. And as you know, probably, that conjecture has been solved already in dimensions 8 and 24 by Coulomb, Miller, Radchenko, and Vyazovska. And so we're just waiting for the conclusion with the proof for dimension 2, which would, in fact, complete the program of proving, for instance, that the Abrikosov lattice, the triangular lattice, is the thing that should emerge from the minimization of the functional for superconductivity, the Ginzburg-Landau energy. Okay, so that's if you're interested in dimensions 2, 8, and 24. And if you're interested in other dimensions, sadly, there is no such conjecture. And in fact, if you're even in large dimensions, you don't think that minimizers will be lattices. There should not be. And so we're left with this conjecture in dimension 2 that the triangular lattice is the global minimizer. And in dimension in that dimension 2, there is a partial result, which is that it's the minimizer among lattices of fixed volume. So that's a sort of old result from the 50s related to the minimization of the Epstein zeta function of the lattice. So minimization in the class of lattices. And in other dimensions, even that is not solved, right? The minimization in the class of lattices, as far as I know, is not proved. For instance, in dimension 3, the proof that it's not proof that BCC is the best lattice or FCC and some other interactions. So that remains difficult questions for number theory, and proving that these things are global minimizers, that's even harder, even more out of reach for now, I would say. Okay, so we've gone from the minimization problem to the mean field distribution, the empirical measure, the equilibrium measure, and then the micro scale. We found that if you zoom, right, you should see these lattices in low dimension, like these triangular lattices in 2D or in dimensions 8 and 24, and other unknown configurations otherwise. And so now I want to spend a little bit of the time left talking about the case with temperature. So what happens when you add temperature to your system? So now, in following the paradigm of statistical mechanics, you look at the Gibbs measure. So it's the probability of observing your configuration at x1, xn is proportional to exponential minus beta times the energy. And you have to normalize by what's called the partition function, which makes this a probability density. Okay, so configurations with more energy are less favorable configurations with low energy are more favorable, but it depends on the temperature, because you also have a question of how many, how much volume in phase space these configurations occupy. So if you know that the minimizer is a triangular lattice, that still doesn't occupy a lot of volume in phase space, so you may not see it very well. Okay, there is also a question of expansion. Instead of expanding the minimal energy, this time you want to expand the free energy. So what is the free energy is what you obtain when you take the log of z and you divide by minus beta. So it's a sort of, if you want, average energy somehow. In physics, it's called the free energy. And again, there is conjectures about expansions of this thing in powers of n, just like for the minimal energy on the sphere. And these coefficients, now they depend on beta. They come with physical interpretations. In theoretical physics, they are related to field theories, and they also have a geometric interpretation that I won't have time to discuss. But again, these things are very unknown, except for A, the leading order, that's easy thanks to the equilibrium measure. And now we have access to B beta, the second coefficient. But the next ones are would be very, very nice to find, to identify. That's open. Okay, so let's start again from the mean field behavior. What do we know at the beginning? The empirical measure. Well, it still converges to the same Frostman equilibrium measure. And now it's almost surely, if you want, it's true, except with very small probability, exponentially small probability. This is phrased as a large deviations principle in the probabilistic language. Okay, so you expect the same distribution, uniform in a disk, for instance. So this is what you find in 2D with the quadratic confinement, 2 different temperatures, uniform distribution of points in a disk. This is what the equilibrium measure tells you. And now let's look a little more precisely at the effect of temperature. You see that the effect of temperature is that when beta, so you remember beta is an inverse temperature in physics, okay? So if beta is very large, it means temperature is very small. So you expect things then to be quite rigid. When beta is very small, it means the real temperature is very large and you expect things to be agitated and shaky. And you see that on the picture, even though the macroscopic behavior is the same, the microscopic behavior feels a difference, right? It's much more shaky on the right-hand side. And we're going to see that again, the effect of temperature. I'm going to decrease temperature or increase beta. So you see distribution, microscopic level is the same. It's kind of uniform in a disk, but you see things becoming more ordered, more and more ordered as I decrease temperature, and eventually maybe you believe that it crystallizes to a triangular lattice, maybe if there were enough points in this picture. Okay, so what are we able to do? We're going to be able to describe things in terms of a limiting point process after blow up. So it's about the microscopic level. You have to blow up and see these configurations. So what you see instead of these triangular lattices or Leech lattices or what, when you have temperature, well, you see random point configurations. So these are called point processes. And here are 2 examples of point processes. On the left-hand side, the Poisson point process. That's a point process where you just throw your points kind of uniformly at random in a box, and there's no interaction between the points. So they can totally fall at the same place. On the right-hand side, you have the Ginibre point process. So this is a unique case in 2D. It's only in 2D when beta equals 2 for the quadratic confinement case, where the limit point process from my Coulomb gas is known, is identified, and people know how to compute its correlations and plot it. So this is a plot of it. And you see it has, it's different from the Poisson point process. The distribution of points is uniform, but you see that the points kind of repel each other like you expect, because you know there is logarithmic repulsion between the points. They don't like to be too close to each other. So there's a certain amount of rigidity here. This is a determinantal point process. It has all sorts of very interesting properties. Okay, so what we can prove is that in these systems, the Gibbs measures, for logarithmic or Coulomb or Riesz interactions, so the same classes of interactions, as long as S is bigger than D minus 2 and strictly less than D, the Gibbs measure concentrates on configurations whose limiting point processes minimizes something, and it's no longer W alone, it's a combination between W, so it's an average of W plus 1 over beta times the relative entropy of the process with respect to the Poisson point process of intensity 1. Okay, so what is Px? Px is the point process you obtain when you zoom around X. Okay, so you remember you have many points around which you can zoom. And then you average, you sum over all these points. So it doesn't really matter this averaging. What I want you to remember is there is just a competition between W and relative entropy. Okay, so now you see the effect of temperature, beta. It will depend on beta. So if beta is very large, then you can sort of neglect this entropy term and you refine the question of minimizing W. Okay, so when temperature is very small, you should minimize W, just like for minimizers. This is not so surprising, it's consistent. And now we expect that we have crystallization. In fact, we have a proof of crystallization now in 1D or in dimensions 8 and 24, thanks to the Kohn-Kumar conjecture proof. Okay, so you can show that now that configurations will concentrate on these crystals. And in other dimensions, well, they will concentrate on minimizers of W, whatever those are. Now, at the other end, when beta is very small, that corresponds to very large temperature, then this becomes the dominant thing in this free energy, and that's what you should minimize. If you want to minimize a relative entropy with respect to Poisson, well, then you should just be Poisson. That's what minimizes the relative entropy. So when entropy dominates, you converge to the Poisson point process, and the Poisson point process corresponds to a non-interacting gas. So that's also natural when you tune beta out in your exponential of minus beta h. In the end, you get just independent points. And you see that for intermediate beta, well, there is an intermediate situation, and you can characterize now these point processes as the fact that they want to minimize this sum of two things. So physicists do discuss phase transitions in dimensions 2 and 3, and they say there is crystallization at a certain beta. And for them, crystallization is a question of speed of the decay of correlations. But their evidence is only numerics, and they don't really agree on whether there is such a finite temperature transition anyway. Okay, so we generalize this to the hypersingular case in work with Doug Hardin and Thomas Leblay and Ed Saf. The case where S is less than D minus 2, that even though it's less singular, remains open as far as I know. A corollary of this is this next order expansion of the free energy. I told you we can access the next order term, and the next order term is given by the minimum of this functional that we have to look at here. So that's settled, and now there remains some next order terms to investigate that we don't know. This is the first time that something like this was done beyond dimension 1. So in the dimension 1 log case, there was a lot of results, but in dimension 2, only formal results. In dimension 3, there was nothing much done. Other results that we obtained and that are restricted now to the Coulomb case only is better rigidity results down to the micro scale. And one of the corollaries of this rigidity results with Scott Armstrong is that we can show existence of a limit point process. That was something that was actually open, even though it sounds strange, but when you look at these configurations with temperature, when you zoom, people didn't even know that there is you can define a limit point process, except for this beta equals 2 determinantal case, this particular case. Now we can show in any dimension in all the Coulomb cases that there is up to a subsequence limiting point process. It would be much nicer to have it without subsequences, but we don't know how to prove that. Okay, so I want to finish with a final result, which concerns the case with a temperature, but also the case without temperature. If you don't like temperature, just take beta equals infinity in my theorem, because that corresponds to minimizers of the energy when you take beta equals infinity. So the thing is still completely valid for energy minimizers. And it's only for the Coulomb case. And at first, it's only in 2D, although now I can get some results in 3D as well. But let's focus on 2D, that's good enough. So these results reveal an even further rigidity of the configurations of points. And instead of like zooming and looking at point processes, here we look at test functions. We take a smooth enough test function f, and we look at linear statistics. So it's the sum of f of xi. So you just sum f over some points, and you compare with the expected behavior of that, the average behavior, which is integral of f against the equilibrium measure. Right? So you know that this should be very close to that. You make the difference. That's the fluctuation around the equilibrium measure tested against the test function. And the slightly surprising result, maybe, is that this converges as n goes to infinity to a Gaussian distribution with a certain mean and a certain variance. Okay, so I told you if you don't like temperature, take beta equals infinity, then the variance is 0. And so it tells you that for minimizers, this thing converges to a certain number. It just converges to that constant. And you see, it's quite strong because here you have n terms, you have a sum of n terms, and here you have a term of order n. And the difference between these two terms of order n is actually of order 1. So it means that the approximation by the equilibrium measure is very, very strong. It's much stronger than what you would get, for example, for IID random variables. If you had a sum of n IID random variables, you would get an approximation by root n. Of order root n, and this time you get an approximation by O of 1. So this tells you why these Coulomb systems, in some sense, are much better at approximation than just IID points, than throwing IID points. Okay, and not only that, but you can even localize these results with test functions that could be supported, that could be sort of shrunk down, zoomed down to any scale. Here that would be much bigger. I should have put much bigger than n minus 1 over 2. So this result only existed for beta equals 2, because that's the determinantal case, or previously for the 1D log case. And now can be extended somewhat in dimension 3 in certain temperature regimes, and you can even let beta depend on n. But I don't want to get into too much detail. And in a probabilistic language, this can be expressed as the fact that the Coulomb potential generated by the fluctuation, so this inverse Laplacian, if you want the H that I was talking about before, convergence to the Gaussian free field, which is this well-known probabilistic object, which is a sort of 2D analog of Brownian motion, random surface. So that is the limiting behavior of the fluctuations. So I will just do one slide on some buzzwords for the ingredients. I told you about the electric approach. So all of this comes up in the proofs of everything I described towards the end. The electric approach, reformulating everything with the electric potential. The screening procedure, which I don't have time to describe, but which allows you to compute things additively over boxes up to some small error. Bootstrap on scales, which is you start by saying, okay, you know things on the macro scale, you know how many points you have, you know how much energy you have. Now you start to go to a smaller box and you show that number of points in that box cannot exceed the size of the box. The energy in the box cannot exceed also the size of the box. And now you go below in scale, etc., and you finish at the micro scale almost. And things are actually bootstrapped in the sense that We do the screening at every step. We get a better free energy expansion, and we use that to get screening at the smaller scale. It's a transport approach for the CRT, so using transport of equilibrium measures. From one equilibrium measure given for a certain potential V to an equilibrium measure for a perturbed potential V. We use that as a change of variables in our computations. And this commutator estimate or functional inequality that I showed you, which also serves to obtain controls on fluctuations for smooth statistics and things like that. Okay, so I will stop here, and I thank you very much for your patience and attention.
Thank you, Sylvia. And then are there questions in the room or in the virtual room? There is a question. Yeah,
I have a question, and sorry if this was answered during the talk, but the Coulombic distance between point sets and measures that you were looking at, are there any estimates of how that compares to, say, phosphine distances?
Did you get that?
Sorry, I didn't get the end of the sentence. Are there any what?
The comparison between Coulomb distance and Wasserstein distance.
Yes, so there are some comparison, but it's not, there is not one good functional inequality, if you want, between the two. They just measure things differently. So you can compare with the one Wasserstein distance fairly easily, but if you remain on a compact set, but between, for example, W2 and Coulomb, they're not comparable. There's not, you know, they are not equivalent norms. So people have tried to write down Coulomb transport inequalities, they call them, in particular the group around Jalil Shafai. But it only works to a point. So I think that there are just very different ways of measuring, even though they have some natural relations in some regime. And actually, I don't know if you've heard this business, and that could interest you. You know, there's a whole line of work around people like Ambrosio and Trevisan and Stra on measuring Wasserstein distance between point processes. Right, so you look at the Poisson point process, and you look at another point process, and you measure the Wasserstein distance, and so it corresponds to it's kind of related to the Coulomb distance in a very particular regime, and so some of what they do is actually not so different philosophically to what is done here. But okay, to close the argument, you can check quite quickly what there is, and you see that except for very nice measures, there's no direct comparison between the two. I hope that answers your question.
It did, thank you.
Okay, yeah. So are there more questions? I had a question. It was a curiosity because you mentioned linear statistics. Are there other kind of statistics that one could measure for these processes to get a result like the last one that you showed, like quadratic? I don't know. I don't have any idea. So, yeah.
Well, I mean, the dream is you want to look at much more general statistics that involve not only 1 point, but 2 points and n points. And then you would get universality results, what they call universality. But that's much harder, yeah. So things that are truly 2 points, that's already, that would be already a big progress.
So that would be a function of 2 variables in your last theorem, or is that something like that?
Yes, if you want. But you have to allow this function to depend on Yeah, I think if your function is very smooth, you can probably cheat and come back to functions of one variable only.
Mhm.
So it's actually important that you let it depend in a slightly non-smooth way of the two variables, for instance.
Okay, that's interesting. Is
But
there
it's
any-
harder. It's immediately much harder. I saw some questions in the chat.
Yes. So,
Yes, there's a very good question. Does the deviation inequality, so you mean the central limit theorem, does it hold for less regular f? So there is a threshold at which it has to stop working. And it's expected that maybe this is for H1 functions. What is clear is that, for example, if f is discontinuous, it should not be true. If you take the indicator function of a set, right? And let's say you start to count linear statistics of the indicator function of a set, it means you're counting the number of points in a set. The number of points in a set, how much it deviates from the, let's say, the area of the set, the volume of the set, that cannot be of order 1. You know that, right? For typical, you will have some boundary effect. It should be of order n to the 1/4 in variance. So you should jump from order 1 to these n 1/4, and there's many conjectures about this, or physics papers, predictions, I would say. And so what is exactly the limiting threshold in terms of regularity of the test function is a very interesting open problem. And you see that here the variance involves the H1 norm. So if you're not at least H1, the variance would be infinite and there's no hope. Is H1 the right threshold? I'm not sure. But yes, there's definitely a very interesting effect of the regularity, the smoothness near the boundary. So the test functions for us that we have, they are smooth and behave like a cutoff, and this cutoff effect is very important.
okay.
And what is the main obstruction? Yeah, it's technical. Yeah, it's when you do the proof, you see you need these transport maps that I was discussing, and they lose regularity if your function is less regular, and so all the estimates, all the error estimates start to blow up. All the errors become too large, and you cannot do anything. And I think it reveals something deep. It's not just a technical. It's not just a technical obstruction, as I said, because it's not true when f is sufficiently irregular.
Okay, thank you. Any more questions? It seems that that's not the case. So thank you again, Sylvia, for the nice overview of this field. Okay, so thanks again.
Thank you.
Okay. Right. So let me stop this.